It's difficult to check whether two schedules leave the database in the same final state. We need an easier test for equivalence. And we're going to settle for a conservative test, meaning one that when it says things are truly equivalent, they indeed are, so it's got true positives. But sometimes it may say, I'm not sure if they're equivalent, and they may in fact be equivalent. So those would be false negatives. That's okay. Whenever this check says, I'm not sure, we're going to reject the equivalence. And whenever it says, I'm sure, we're going to accept the equivalence, which means we'll only accept true equivalences. Now, the effect of not being sure and rejecting equivalences means that there may be some schedules that do leave the database in the same final state, but we're not going to be sure if they're equivalent, and we'll say maybe they don't. And the result of that then is to sacrifice some potential concurrency. There's an interleaving that would have worked that we're going to reject. So be it, because we're going to have a quicker and easier correctness check. Okay? We're going to use a notion in this of two operations conflicting, and those operations will be reads or writes. And the definition we'll say is that two operations conflict if they satisfy three properties. First, they're from different transactions. Second, they're on the same object. And third, at least one of them is a write. And I'll assert, and you can prove this to yourself pretty easily, that the order of non-conflicting operations has no effect on the final state of the database. Okay, so for example, two different reads, it doesn't matter what order the reads happen, they have no effect on the final state of the database. However, the order of a read and a write from two different transactions can have a big difference, because whether the read happens before the write determines what the read reads. Okay, we're going to focus our attention only, therefore, on the order of conflicting operations, and we're free to reorder non-conflicting operations without worrying about the effect on the final state of the database. Using this intuition, let's do some redefinitions of the things we've seen before with slightly different names. So we'll say that two schedules are conflict equivalent, not equivalent, but conflict equivalent, if they involve the same actions of the same transactions in the same order, and every pair of conflicting actions is ordered the same way in the two different schedules. And we'll say then that a schedule S is conflict serializable if it is conflict equivalent to some serial schedule. And if S is conflict serializable, then we know it's also serializable. Because if it can be shown to be conflict serializable, that means that the only difference between it and a serial schedule is the order of non-conflicting operations, which we said have no effect on the final state. Okay? So conflict serializability is a conservative test for serializability. Note that it is conservative, which means that some serializable schedules are not conflict serializable. So conflict serializability can give us some false negatives as a test for serializability, and that's the cost of a conservative test, the price we pay to achieve the easier enforcement that conflict serializability is going to give us. Let's look at an example for some intuition. We're going to slightly reword our notion of conflict serializability here to something even simpler. We're going to transform a schedule S into a serial schedule by swapping consecutive non-conflicting operations of different transactions. Remember that the order of non-conflicting operations has no effect on the final state, so any of these swaps we do has no effect on the final state of the database. So here's a schedule in the string format with reads and writes from one transaction in red and from another transaction in blue. And we've actually separated the red and blue transactions vertically a little bit to make this easier to see. Now, here's that same transaction, but we're going to start manipulating it by swapping consecutive non-conflicting actions. And we're going to keep the original transaction up in the box so we can compare. Okay? So the first swap we're going to do is we're going to swap the read of B and the write of A. Those are non-conflicting because they touch different objects. Right? And so it doesn't matter what order we do that write and that read. The read will read the same value in B, the write will write the same value in A. Now, we can also swap the write of B and the write of A across the two transactions, because no matter what order we do those in, they have the same effect on B and A. They touch different objects. And we can swap the read of B and the read of A. Two reads have are not conflicting. And then finally, we can swap the write of B and the read of A because they also have no conflict. They're on different objects. And you can see here we've achieved a serial schedule at the bottom, and we achieved it only by swapping non-conflicting operations, which means that the original schedule up at the top is conflict equivalent to the serial schedule at the bottom. And that means the original schedule is conflict serializable. So here's another example with two transactions, one in red, one in blue, written from left to right. And the question is this schedule conflict serializable? And you'll see that there's conflicts all over. So the two writes of A conflict with each other. Red's read of A conflicts with blue's write of A. Blue's read of A conflicts with red's write of A, and the only things we can swap here are the two reads. And as a result, it's not possible to get a conflict equivalent serial schedule here. And so this is not conflict serializable. Let's dig in deeper to see how we can prove this kind of property of not being conflict serializable in a more robust way.